have mentioned in the previous section that this specific series, the sum of log k over k, doesn't necessarily require invoking the integral test in order to determine its convergence. And so what I meant was the following. So for k bigger than or equal to 3, bigger than e, right? So if k is at least 3, then log k is bigger than 1, and log k over k is bigger than 1 over k. Right? So this equality holds for k at least 3. So what happens if we take this equality and sum both sides for k greater than or equal to 3? In other words, we apply the summation like so. So because every such term, log k, is bigger than 1 over k, then if we sum them up like so, log k over k from 3 to infinity is bigger than the sum of 1 over k from 3 to infinity. But we know that the series on the right is divergent. So if the summation were occurring from k equals 1 to infinity, then it would be the precisely the harmonic series. So we would know that it's divergent. Now this is harmonic series without the first two terms. We know that any finite number of terms have no impact on the convergence of a series. So removing the first two terms does not change the fact that harmonic series is divergent. And so the sum in the right hand side is equal to plus infinity. So we have this infinite series. It's bigger, well, in fact, it has to be bigger than or equal to plus infinity. And so it follows that the series in the left-hand side is divergent, which is precisely the conclusion that we obtained for this series. So you can see that instead of applying the integral test, we could have arrived at the answer much faster if we simply compared this new series to the one that we already studied previously, 1 over k. Right? And so the principle that we used here is called a comparison test. And I will next formulate the precise statement of this comparison test. So comparison test applies to terms with to series with non-negative terms. And it goes like this. So suppose you're given two series the sum of AK and the sum of BK, where we will assume that the summation occurs from k equals 1 to infinity. But the same statement applies for any range of summation, and you will see how to transfer the statement of this comparison test to that range of summation. Suppose you have two series, and they are such that both AK and BK are positive, and the terms BK are bigger than or equal to AK. Under these assumptions, if the series with the bigger terms, so if the sum of bk, k from 1 to infinity, converges, then so does the series with the smaller terms. Because the only way for a series with no negative terms to diverge is to diverge to plus infinity, and the fact that the infinite sum of bk's is finite means that the infinite sum of ak's is also finite. It's bounded above by the sum of bk's, and then we have a sum with no negative terms bounded above, therefore it must converge, again by the theorem for monotonic bounded sequences. You just need to apply this theorem to the sequence of partial sums of ak. Now, if on the other hand the series with the smaller sum, with the smaller terms, diverges, then so does the series with bigger terms. And this again makes sense if summing up the smaller ak's already gives you plus infinity, then summing up the bigger bk's will certainly give you plus infinity as well. So I should emphasize that this comparison test requires that the terms of your series are non-negative, and only then you can apply the test. But as we have just seen, this is a quite useful convergence test because it allows you to reduce new series, the question of convergence for new series, to the question of convergence of some series that you have already studied. So in this case, for example, we reduced this new series to the harmonic series, and we were able to give the answer quicker than when applying the integral test. And so this is the statement of the comparison test. We will then discuss some examples of its applications.